Today we're going to be looking at lenses, focusing, if you'll pardon the pun, on converging lenses. We'll start by considering the uses of converging lenses, the shape and properties of a lens, and how we can draw accurate ray diagrams to describe the properties of lenses. We will end by building a simple telescope. Before studying how lenses actually work, students should have studied refraction. They should know that refraction occurs when a ray of light travels between mediums of different optical densities, and that this occurs twice if we consider a ray of light travelling through a rectangular block. Refraction occurs at the boundary from air to glass, moving towards the normal, and then again from glass to air, moving away from the normal. Let's have a look at this cross-section of a lens. If we consider the top part of this image, you can see there is refraction occurring on the left-hand side, and a separate refraction event occurring on the right-hand side of the lens. If you consider the ray of light that is travelling straight through the middle of the lens, then you can see that as it is approaching the lens along its normal, at 90 degrees to the surface, there is no bending of the light due to refraction. Most lenses we consider are discs of glass or plastic, and they can bend light coming in from the top and the bottom and the left and the right. When we are using ray boxes, we end up using lenses that act only in one dimension, but they can still be used to demonstrate focal length, and they have many similar properties of a disc-like lens. We can find lenses all around us, and we can expect students to be able to recognise and identify lenses. They're in the cameras in our phones, they're at the front of our eyeballs, the glasses or contact lenses we wear are bespoke lenses designed to help us. There are lenses at the front of projectors that we use in our classrooms, and students will also be familiar with them from less day-to-day examples like magnifying glasses, microscopes and telescopes. What may be counterintuitive is that a single type of converging lens can be used to do multiple different things, depending on how it's set up. A really nice way to start a lesson on lenses is just to give each student a single lens and ask them to investigate it, to play with it, to look through it, move it closer and further away from their eyes, to hold it up to the windows and generally to get used to what it does. If you've never done this before, it's really worth doing. Here are 3 ways that the same lens can be used with different effects. I could hold it up a few centimetres away from a piece of paper, and I'm using it as a magnifying glass. I could hold the lens up close to my eye, and I can look through it. If I get it in the right place, I can see what's behind it, although it will be a different size, and the image I see will be inverted, i.e. upside down. Thirdly, I can hold up a lens close to a piece of paper and project an image of the bright object a distance away onto that paper. When I was taught about lenses first, I was taught the terms concave and convex. I had a little mnemonic technique that I used to help me remember which was which, that the concave lens had a shape that curves inwards, like a cave. But if you look at the profile of some spectacles, it may not be obvious whether this is a concave or a convex lens, because it curves in on one side and it curves out on the other. So a better way is needed to describe the lens. The result of all of this is that it's usually clearer to describe the properties of the lens by describing whether it bends the light inwards, in which case you would describe it as a converging lens, or if it bends the light outwards, in which case you would describe it as a diverging lens. Let's have a look at an extra way we can describe this converging lens. If we picture an object being so far away on the left-hand side of this diagram that by the time light arrives at the lens, the rays are pretty much parallel to each other and to the principal axis, then we should be able to see that with this lens in place, it is focusing all the light into a single point. This is the principal focus. When you are using parallel rays of light, the distance from the vertical axis of the lens to the principal focus is the focal length of the lens. In this case, you can see the focal length is 8 centimetres. Now what does it mean? Does it mean this lens is always going to focus at 8 centimetres? No. It means that if light is coming from an object that's a very long distance away, then it will focus it at 8 centimetres. But if the light is coming from a source that's closer, then the light will be focused on a different place. How can you easily find the focal length for a normal lens? Well, the easiest way is to position yourself a reasonable way away from a window or other bright light source. This is easier to do in a school lab than it is to do in my house, but if you can get around 5 metres away from the window, then it should work really well. Hold the lens up in front of a piece of paper, with the lens pointing in the direction of the window. Now move the lens in and out towards the paper until the image is focused. If you measure the distance between the paper and the lens, you will find the focal length for your lens. The common focal length of lenses in a school lab range from about 5 centimetres, which will be quite a chunky lens, to around 1 metre, which will be a very thin lens. Some school technicians colour code their lenses by focal length. They do this either by using a Sharpie to colour the edge of the lens, or by putting a very small sticker somewhere close to the edge of the lens. This can save quite a lot of time when trying to organise your lenses at the end of a lesson. The really nice bit about doing this experiment is that it produces a colour image. This always seems to surprise and impress the students. The image is inverted. A nice way to demonstrate this is to have one student standing in the window waving their arms above their head. Once students understand how to work out the focal length of the lens, I ask them to consider how, if you change some of the properties of a lens, it will affect its performance. The first question I ask students to consider is what will happen to the focal length if I increase the size of the lens but keep the curvature the same. Try and think about that now. Pause the video if you need time to think. The answer, perhaps surprisingly, is that not very much happens at all. By increasing the diameter of the lens, we are gathering more light, so the image that we create will be brighter. However, if the lens has got the same curvature as before, then the focal point will be in the same place as before, and the focal length is therefore the same. So the advantage of having a really wide and chunky lens attached to your digital SLR camera may not be able to increase the distance you can view or the level of zoom, but it will gather more light and give you a better picture or capture sharper images by enabling shorter shutter speeds. The second question is what happens if I make the lens curvier? That is, what will happen to the focal length if I make the lens fatter in the middle? Pause the video if you need to. The answer is that the focal length is brought closer to the lens. The focal length decreases. In my experience, most students get this right. We can go back to explanations about how lenses work with refraction. We can see that the rays of light are going to be hitting the surfaces at larger angles away from the normal. This means that more refraction is going to occur. The final question I ask is what alternatives are there to fattening the lens? Imagine if we are told that we need to wear glasses, but the lenses we are offered are really chunky and vanity prevents us from wanting to wear them. Well, what can we do? Well, most glasses wearers know that the alternative is to buy extra thin glasses with lenses made out of different materials. But how do these work? By having a higher refractive index, we can achieve the same effect as having fatter lenses. The advantages could be having lighter and thinner looking glasses, but the disadvantage is usually around cost, because opticians charge more for glasses made from a material with a higher refractive index. I wore glasses as a child through to early adulthood, and I dreamed of the day when I could buy glasses made out of diamond. I realised that cost may be an issue, but the advantages were obvious to me. They would be almost impossible to scratch, and they would also be incredibly thin, because diamond has got an astonishingly high refractive index of over 2.4. What actually happened is I bought laser eye surgery on eBay for £600 in my early 20s, and I haven't looked back since. Let's consider how we draw ray diagrams for lenses. You can teach this in a number of ways, but I tend to do it with a virtual simulation of a lens, so that I can change many of the variables that I need to do. Today, I'm going to use a Desmos simulation of a lens. In this simulation, we've got an object on the left-hand side, we've got a lens in the middle, and at the moment, we are creating something called a real image on the right-hand side. What do we mean by the term real image? Well, I like to describe it as a real projectable image. This means that if I hold up a screen or a piece of paper where the real image is, what would be created would be a picture of the object on the left-hand side. I'm going to move the lens around and I'm going to move the object around. And I want you to look at what's happening to the rays of light that are coming off this object and how they are interacting with the lens. With a class, I'll ask the students to consider light coming from the same point at the top of the object. Actually, light is bouncing off non-luminous objects, will be scattering in every direction. But to do the calculations and our drawings, we only need to draw 2 of them. Half of the students will consider what happens to a ray that comes out horizontally, and the rest of the students will consider the ray that passes through the middle of the lens. And I will continue moving it around and ask students to create a set of rules that governs what is happening to their rays. Usually, with a bit of support and time, students will be able to spot the patterns for themselves. This is crucial to them being able to draw ray diagrams for themselves later. Pause the video if you'd like to try and write down the rules for yourself. Here is how I describe the rules to my students. Pick a single point on an object next to a lens. Draw a straight line from the object directly through the centre of the lens and out the other side. Draw a horizontal line from the object to the lens, then from this point of the lens through the focal point on the other side. Where these two lines meet will tell you where an image has been formed. The reality is slightly different, as we discussed earlier, but we consider the lens to be thin and show refraction occurring from the plane of the lens. Now, will these simple rules describe all the cases that we were looking at before? Yes, I think they will, but we'll need to make that explicitly clear to students. First of all, let's consider what happens to light that hits our eyes. In this case, we have an object a reasonable distance away, certainly much further away than the combined focal length of the cornea and the lens in our eyes. The real image that is then projected onto the retina in the back of our eyes is an inverted image, and it is substantially smaller than the original object. As objects move closer or further away, the ciliary muscles around the lens change the lens's shape, and therefore its focal length, to make sure that the real image that is being projected onto the retina is still in focus. The retina is covered with rods and cones, sensors, which have a short-term chemical reaction with the light, which then send a signal to our brain to tell us what we've seen. We can ask students to figure out why we don't see everything upside down. Well, the signal goes to our brain and your brain knows to interpret it the correct way up. And this is the same thing that happens in a camera. A lens or lenses will focus a real projected image onto a panel of sensors that detect the light. What happens if we bring the object much closer to the lens, between 1 and 2 focal lengths away? Well, this is what happens in a projector in a classroom. There is a very bright LCD display, or 3 displays of red, green and blue, which are mixed together through some clever use of mirrors, and this display is placed close to a lens. If you then put a screen a distance away, then the real image that is formed will be larger than the image on the screen and will also be inverted. Again, we can ask students to figure out why what we look at on a projector screen is not upside down, and the answer is that the displays inside a projector will be configured to show the image upside down so that the final real image on the screen is the correct way up. If you want to move the screen you're projecting onto, then the image will go out of focus. Because you can't adjust the shape of the lens in a projector easily, they have adjustments that enable you to move the lens closer or further away from the internal display to focus them. Something significantly different happens if we now bring an object that is even closer than the focal length. The lens is not strong enough to focus the light onto a point anymore, so we do not get a real projectable image. You could hold a piece of paper on the right hand side until you are blue in the face, but you'll never get a nicely in focus image appearing. What we do get is a change to the path of the light. It now appears to someone who is looking towards the lens from the right hand side that the light is not coming from the object itself, but is actually coming from a larger object placed slightly behind the real object. This is how a converging lens is used as a magnifying glass. Notice how all the same rules apply. You can still identify a line coming out horizontally from a point on the object, which then intersects with the vertical axis of the lens and then goes through the focal point. You can also see a ray of light that goes from the same point on the object all the way through the centre of the lens and continues in a straight line. The point at which these two converge isn't on the right hand side, but is actually on the left hand side, and it is from here that it appears the light is coming from. This type of image is called a virtual image, where an observable image can be viewed as if it were diverging from a different place to where it's actually diverging from. Mirrors, another example of virtual images. In my experience, students find these rules surprisingly hard to apply in reality. The best way to teach it that I've found is to start by showing them virtual simulations and letting students have a play with them. You can then demonstrate the processes to drawing out the ray diagrams to figure out the positions of real or virtual images by doing an example or two under a visualizer, perhaps at the same time as your students are doing the same example. But ultimately your students need to practice for themselves, with worksheets, examples, many of which you can find online or you can create for yourself. Building a telescope from 2 different lenses is actually surprisingly easy, if you don't mind that the image will be upside down. To build a telescope, you need 2 lenses with different focal lengths. Today I'm using one lens with a focal length of 5 centimeters and one lens with a focal length of 30 centimeters. Of course, if you don't know what the focal length of your lenses are, you can work them out in the way that I described earlier. To get a basic telescope working, all you have to do is hold the 2 lenses a distance apart that equals the sum of the focal lengths. So in this case, I would hold them 35 centimetres apart. By looking through the lens with the shortest focal length, I have built a telescope. Of course, this is not very practical, so when I'm doing it with students, I get them to build them on a meter ruler so that they can hold their lenses in place and move the telescope around. Sometimes I've been in schools that don't have any holders for the lenses, in which case some lumps of plasticine can hold them in place. But there's always a chance the lenses are going to fall on the floor and smash, and plasticine covered lenses aren't very nice to hold afterwards. I really like these metallic lens holders that you can slip around the meter ruler and which clamps each lens in place. To make sure that the student telescopes are working well, you can print off an eye test, or just any written text, in a range of different sized fonts, which you can attach upside down to a tree or lamppost outside of your classroom. Students can then test their telescopes. In my case, I've gone from 5 centimetre to 30 centimetre focal length, which is increased by a factor of 6, so the magnification of my telescope should be 6 times. To conclude, we've got to consider the behaviours and uses of lenses in a range of different contexts. If we are careful, we can link this understanding to the skills of accurately drawing ray diagrams. Thank you very much for watching.